the lowest possible grade, the lowest grade I ever gave on the presentation was a -35. Because because we used to do it over several days when I had lots of groups. I had 8 groups. He didn't show up for his own presentation, but he also didn't show up for any of the other 7 presentations, and you lost 5 points for every other presentation you didn't show up for. So he got a -35 averaged into his end grade. That didn't end well. You really should show up to your own presentation.
Hey, I think odds of us not getting a -35 are looking pretty good.
I'll be there. I'll show up. That'll be exciting.
There you go. You see, that's
35 points. Right there.
that's the first step in the battle, is showing up. Yeah, I've had people like frantically calling their last, group member 2 minutes before the presentation, going, "Where are you?" Yeah, showing up. It's always good. All right, let's talk about sugars. We don't have a whole lot of time to talk about sugars, but I'm going to not, go into a lot of detail on here. So, Fischer projections are used for sugars just as they are for amino acids. So we have our chiral center. The simplest sugar is 3 carbons long, and this would be the D isomer. D-glyceraldehyde, right? The D part, the capital D part, means that this OH group is on the right. And that's whatever the highest numbered chiral center here is. So in this case, there are only 3 carbons. There is only 1 chiral center. 2 is the highest numbered chiral center and the only chiral center. So it's on the right. So you also could have L-glyceraldehyde, and L-glyceraldehyde would have the OH on the left. The capital D and the capital L has nothing to do with the direction of rotation. It happens that D-glyceraldehyde in fact is dextrorotatory and that L-glyceraldehyde is in fact levorotatory, but that's purely by chance. Right? So this is also dextrorotatory. And originally Fischer got lucky. He knew that glyceraldehyde, the isomer he was working with, was dextrorotatory, so he knew it was small d. He did not know whether the OH group was on the right or the left, so he took a 50-50 chance and guessed and put it on the right and called that D, capital D, glyceraldehyde, and it turns out he was right, so he got lucky. If you go to the next series of sugars, where you have 2 chiral centers, it turns out that they're both minus. In fact, all 4 of the possible, 3 of the 4 possible pentoses are also levorotatory. So we've got 2 chiral centers. It's carbon 3 that determines whether it's the D or L, capital D, capital L. Both of these, however, are small l levorotatory. I don't really care if you know that. I mean, it happens that they're both the minus isomer that rotates plane polarized light counterclockwise, levorotatory, but that's not something you really need to worry about. You do need to know, obviously, that this one would be levorotatory. How do I know for sure that that L, capital L isomer of glyceraldehyde is levorotatory? It is actually the minus isomer. So if I wanted to write this, I would write this as L minus glyceraldehyde. capital LL because the OH group is over here, and it's small l, L because it's levorotatory. How do I know for sure that that's levorotatory? Just by drawing it. What's the relationship stereochemically between this one and that one? That true? Which one's which? So to do that, we first want to do the bow tie conversion to get everything like in the dashes and wedges. And then we want to do the flop into the plane of the page. And it makes sense to flop it such that the hydrogen goes back. Right, so that is that written in the three-dimensional, and I flopped it so the hydrogen is back, so I'm looking the right way down the bond. OH is 1. Carbon that's bonded to oxygen twice is 2. Carbon that's only bonded to oxygen once is 3. So that would be the R isomer.
Do we have to do the bow tie one?
Not if you're good at just flopping it into 3D without going through the bow tie conversion. But converting it to this first is more foolproof. So obviously that'll be S. If you're good at visualizing in 3 dimensions, you don't really need to do any of that. You just mentally put yourself back behind the board, look out at that hydrogen, and then you can trace your motion from 1 to 2 to 3. So that's the R stereocenter, that's the S stereocenter. There is only one stereocenter, so what is the stereochemical relationship between capital D glyceraldehyde and capital L glyceraldehyde?
I don't know what you're really asking.
What kind of isomers are they? They're enantiomers, right? And enantiomers always rotate plane polarized light by the same magnitude but in opposite directions. So if I knew that capital D glyceraldehyde is dextrorotatory, capital L glyceraldehyde has to be levorotatory because they're enantiomers, right? I can't say anything about where capital D Erythros would be, right? Because it now has 2 chiral centers. It's not a stereoisomer of D glyceraldehyde. It's got 2 chiral centers. Are they both R? This one is, right? You're looking this way, 1, 2, 3. 1, that's 2 because it's a secondary alcohol, that's the primary alcohol, so yes, right, those are both R isomers. This is still the R stereocenter, this is the S stereocenter. What's the stereochemical relationship between D erythros and D threose? Obviously, they're not enantiomers, right? Because if they were, they would rotate opposite, but they don't. They're both levorotatory. They differ at 1 chiral center of 2. So these are diastereomers. So how was Fischer able to determine that erythros had the 2 OHs on the same side and threose had the OHs on different sides, right? How is he going to figure out which one's which? So that's an interesting question because there's lots of isomers of these sugars. Once you go up to the pentoses, right, with 3 chiral centers, there will now be 4 isomers in the D series and 4 in the L series because there's always 2 to the n possible stereoisomers. So with 2 chiral centers, there's 4 possible stereoisomers, D erythros, L erythros, D threose, and L threose. How are we going to figure out which one's which? We got lucky and guessed, right, that this one happened to be the dextrorotatory isomer, and we assigned the capital D. We don't have to get lucky on the rest of them. So what we're going to do is we're going to take the aldehyde of the D series sugar, And we're going to make that into a cyanohydride by adding HCl and NaCN. And that will create a new chiral center. This chiral center is going to stay the D isomer. But we're now making a new chiral center here. Let me put that in the printed page. So we know this stays the R stereocenter because we didn't change it, but we've introduced a new chiral center here. Is this one the RH S isomer? Carbon that's attached once to oxygen beats carbon that's attached 3 times to nitrogen because oxygen beats nitrogen. So that one has to be R. So now what we need to do is convert this cyanide group, this nitrile, into the aldehyde. So how do we convert a nitrile into an aldehyde? The way to convert the nitrile into the aldehyde is to hydrogenate it. But we want to make sure that we only hydrogenate the triple bond and not the rest of it. So we're relatively low pressure. And we use barium sulfate. We have barium sulfate in there as kind of our catalyst poison. So we've got our palladium on carbon. Sorry, we got our palladium, but we've got our palladium on barium sulfate instead of on carbon as a catalyst poison. So that's going to reduce only as far as the CN. And then it's going to stop. And if we put into this reaction mixture some aqueous acid as well, we will create the amine and then simultaneously hydrolyze the amine. So it'll actually go through this intermediate and then hydrolysis of that amine will generate the sugar. Look like the S1, right? So that'll make the 3-ose, and then the other one, treated the same way, will make the erythros. Not too far. So how do we then figure out which one's which? The trick to that is that these aldehydes are oxidizable. So if we were to take this and treat it with HNO3 as an oxidizing agent, that oxidizes off both the aldehyde and the primary alcohol, but doesn't touch the secondary alcohols. All right, so one comes from here, HNO3. Treat this one with HNO3. And make that. By oxidizing the two ends. These are called aldoric acids. So we've elongated the chain. This is the Kiliani-Fisher chain elongation. By making a new carbon-carbon bond to make the cyanohydrin and then selectively reducing that cyanide group to the imine and hydrolyzing the imine to generate the aldehyde. These we can tell apart. How are we going to tell those two isomers apart? What's the stereochemistry? Are these still both R stereocenters? This one is, right? 1, 2, 3. This one isn't. We've just changed our priorities. This is now higher priority than that. So now that's the S stereocenter. So one of those is the SS isomer, the other one is the RS isomer. They're diastereomers still. How are we going to distinguish these two? So we can tell which one came from which. So these are 2,3-dihydroxy succinic acids. And you may remember from the first semester when we did resolution that these are called tartaric acid. So one of those is optically active and the other one is not. This is the meso compound. This one has a chiral center right down there, so this is achiral and doesn't rotate plane polarized light, where this one does. So by doing the Kiliani-Fisher chain extension to add that additional chiral center and lengthen it from a 3-carbon sugar to a 4-carbon sugar, oxidizing with nitric acid to make the dicarboxylic acid, and then measuring the optical rotation, the one that came from this aldehyde is going to be optically inactive. The one that came from this aldehyde is optically active, and that allows us to go backwards and figure out that this chiral center had the OH group on the right, and this one had the OH group on the left. We can pull the same trick, right, by elongating it again to make 5-carbon sugars, and try to tell which 5-carbon sugar is which. It's also possible to oxidize the aldehyde function without oxidizing the primary alcohol. So if instead of treating that with nitric acid, you were to treat that with silver nitrate and ammonia, this is called the tolerance test, you'll oxidize that up to the carboxylic acid, leave the primary alcohol alone, and you will get solid silver or a silver mirror, and so you'll be able to tell that the sugar was oxidizable. This is called a reducing sugar. Because it has the free aldehyde, which is subject to oxidation, we've reduced silver plus 1 to silver metal in the process. So you can tell if the sugar has a free aldehyde function or if that aldehyde function is involved in bonding by testing it with the tolerance test. The other thing you can do is you can test this with a copper solution, Cu2 plus in solution, and you get a brick red. This is virtuous failing solution. These two reactions, the tolerance test and failing solution, were right at the tail end of chapter 17. I skipped them at the time because they weren't that important. But they are important ways of determining whether a sugar actually has the free aldehyde, whether it's a reducing sugar. So we can take that erythros, we can do that Kiliani-Fisher chain extension by adding ACN and HCl, followed by the hydrogen gas, 5 atmospheres on palladium and barium sulfate. And we can extend that chain to get 2 isomers. Both D-series sugars, right, because that's still there. But we've introduced a new chiral center in addition to the 2 that were there in the threose. One of these is ribose, the other one is arabinose. This is D-arabinose. This is D-ribose. Can we tell D-ribose and D-arabinose apart? If we were to oxidize this one up with HNO3, we would generate something with a plane of symmetry down the middle. That would be a meso compound. It would be achiral. Whereas if we were to occupy this one up with HNO3, that would be chiral. Right, because it's not a meso compound. These differ at one stereocenter. They're the same at 2 stereocenters, but differ at just this stereocenter. And these are called epimers. Diastereomers can differ at 1 or more chiral center, and enantiomers have to differ at all of them. Epimers differ at only 1 chiral center. So epimers are a subset of diastereomers that gives you a more precise stereochemical relationship. If you've been working on the project, you've probably been noticing that we usually don't write ribose as the open chain form. We usually write ribose like this, where we have our sugars, like this, and then this is where the base is attached, but when you write them as this kind of ring form with your substituents on the vertical, this is referred to as a Haworth projection. And it gives you the relative position. I'm going to rewrite that and make that a little neater. Carbon 1 here is referred to as the anomeric carbon. That's this carbon. And what we've done is we formed a cyclic hemiacetal. It's an equilibrium reaction. And again, we formed a new chiral center. So it's possible to have two different isomers of that chiral center at carbon 1, which used to be the free aldehyde. So we've actually got an equilibrium going on between the free aldehyde and the two possible isomers, one where the OH is down, the other one where the OH is up. That new chiral center is referred to as the anomeric carbon. And these are referred to as anomers. So if the one chiral center that's different is the carbon that used to be the aldehyde, that's the anomeric carbon, and those are two anomers. The one where the OH group is on the top of the molecule is the beta anomer, and the one where it's on the bottom of the molecule is the alpha anomer. So you can do the same thing, right? We could elongate this one. One of them would have the OH on the right, and that would oxidize to a meso compound. That's D-allose. The other one would have the OH on the left, and that would oxidize to a chiral compound, and that's D-altros. So we can keep building them up and figuring out which one's which so that we can characterize each of them. It's not necessary for you to know the structure of every sugar. The ones you probably want to know are ribose, because ribose is kind of important in DNA. You probably want to know glucose, because glucose is one of the key sugars. So this is glucose. Has it on the right, on the highest number chiral center, which is carbon 5. So this is what makes it a D isomer. And you probably want to know the isomer that differs at chiral center number 4. That one is D-galactose. still the D series sugar because this OH is still on the right. But it is a C4 epimer of glucose. Galactose is one of the two sugars that's present in milk sugar. The two monosaccharides that's present in milk sugar, aka lactose, which is an important sugar. Haworth projections are fairly commonly used in sugars, but they're not really a very good representation because the ring isn't really planar. So what you'll find is that usually the sugars are actually drawn as a chair form. So if you are D-glucose in chair form, you look like this. This would be beta D-glucose. And beta D-glucose is in equilibrium with alpha D-glucose. Where the OH group is in the axial position in the alpha isomer, and the equatorial position in the beta isomer. You'll notice that all of the other groups are equatorial in glucose. So carbon 2, 3, 4, and 5 have equatorial groups. Probably why glucose is one of the more common ones. It's the most stable. The difference between D-glucose and D-galactose is that C4 epimer so the enzyme that allows you to digest the glucose doesn't necessarily allow you to digest the galactose because that OH group is in a different spot. Which one of those is more stable? Beta or alpha? Beta, this one's more stable. So the beta isomer has a rotation of positive 18.7 degrees, and the alpha isomer has a rotation of plus 112 degrees. The equilibrium mixture of the two has a rotation of plus 52.7 degrees. Can we use that information to determine what the ratio of those two isomers is to anomers? The open chain form is only about 0.03%. Almost all of that sugar exists in one of these two 6-membered ring cyclic hemiacetals. Which number is 52.7 closer to? 18 or 112? So it's definitely going to be that one that's major, right? But can we determine the ratio? Yes, obviously we can. So let's let X equal the percentage of the beta isomer. And let Y equal the percentage of the alpha anomer. We know that X plus Y is equal to 1 because almost none of it is in the open chain form. But we also know that 18.7X plus 112y equal to 52.7 because if we take the percentage of it that's rotating 18.7 and add that to the percentage of it that's rotating 112, we have to get the overall rotation. Simply set this, y is equal to 1 minus x. Plug that in here, 18.7x plus 112, 1 minus x equals 52.7. 18.7x plus 112 minus 112x equals 52.7. 112 minus 18.7 times x is equal to 112 minus 52.7. Solve for x. And if you do that, you'll discover that the beta isomer, I think, is 64.6% maybe. Something like that. I can't remember exactly what the answer is. It's roughly 65, it's roughly 63 to 37-ish. So it's not quite a 2-to-1 ratio, but it's similar to a 2-to-1 ratio, where that additional equatorial hydroxyl group is significantly more stable. I was going to talk a little bit about disaccharides, but we don't have any more time, so I'm not going to talk about disaccharides. It is actually possible to isolate the pure alpha anomer and the pure beta anomer, because one of those crystallizes from water if you do a recrystallization from water, but if you recrystallize it from acetic acid, you get the other one. So you can get the two solids pure. When you dissolve them into solution, they'll start out at plus 18.7 and then gradually change to 52.7. Or they'll start out at 112 and gradually change to 52.7. That phenomenon is called mutarotation, and it's talked about in section 4. Is that about right? 63 to 37-ish?
63.6 and 36.4.
Yep. I think one of the suggested problems asks you to do the same calculation for galactose. That's it.